Okay, we are entering chapter 2. Let me just write down there. Chapter 2. We are entering chapter 2, and then this is going to be a chapter on kinematics. Okay, so to begin, I want to mention that the difference between kinematics and dynamics is that kinematics, you only care about the motion. You only care about the motion, or basically how it moves. Whereas dynamics, you are caring about why it moves. Okay, what I mean by why it moves, am I saying, okay, is it related to gravity, right? Is it related to friction? Was there a collision, and so on and so forth? Okay, so I want to focus on kinematics, right? I want to focus on kinematics. And in mathematics, we do have a bunch of equations that relates our observations to quantifiable measures. So to begin, in SPM, right, we have covered the difference between velocity. Sorry, we have defined velocity, we have defined acceleration, we have defined displacement. So displacement doesn't change, right? Let's use S as displacement. We have defined displacement, right? But now we want to take the first two, and we want to further split them up. So what we do is we are going to B comma A, we're going to split them into two. The first one being an average value, and the second one being an instantaneous value. Instantaneous value. So we can say average velocity or average acceleration, and then we can have instantaneous acceleration or average acceleration, right? So when we talk about average, let's just define here. Okay, so when we talk about average, oh, can't spell that. Okay, so when we talk about average, what we mean is between 2 points in time. 2 points in time. Now, what that also means is that we disregard between them. So let's say I have an equation, right? An equation for, let's say we have a graph for displacement. So ST graph is just displacement against time. Let's say I have 2 points. I have 2 points in time. So let's call this and this 2 points in time. Let's call this one and initial and final. So let's call this to be as final, as initial. Let's call this time final, time initial. If I would talk about average, being average velocity, right? I'm just going to change colors here. There we go. Okay, if I were to say V average, what I mean by that is just going to be my final displacement minus my initial over my TF, again, final time, minus my T initial. That's what it means. It simply means the change in displacement over the change in time. Now, if I were to take a different route, let's say I take a different route, if I were to do this instead, my average value does not change. My average value is still going to be delta S over delta V, delta T, sorry. Delta S is still over delta T, okay? It doesn't change. It is independent of the route that I take, okay? Now, if I were to talk about instantaneous values, so let's again start instantaneous value. What I mean by that is going to be a single point in time. It's going to be a single point in time. So that means the path does matter. Okay, so again, I'm going to have an ST graph. Okay, okay, that's not a problem because that is a constant velocity. So constant velocity, constant velocity. So the gradient is equal at all points. However, if I have a different route, so let's say I have a different path, let's take this instead, right? If I were to take a single point in time, so t1, okay, I will have to draw a straight line that is touching that point, right? And then I need to determine what is the value of that gradient. So the gradient of that line. Okay, so this simply means my instantaneous velocity is going to be my ds over dt. Okay, that's what it means. That means that in instantaneous case, you have to use calculus in general. You will have to use calculus because it's a single point in time. You don't have any range to work with. Okay, so what we can conclude from this is that for average, you need 2 points in time. You always need 2 points in time. Okay, whereas in the case for instantaneous, you have a single point in time. So if the question says calculate the average velocity between time equals to 5 seconds and time equals to 3, then you will use average velocity, that you're asking for average velocity. But if they're asking for what is the velocity at, so the word here is at t equals to t1, then you have to use instantaneous case. Okay, and this goes for acceleration as well. It's just that for acceleration, you might have VT graph instead. Okay, for acceleration, you have VT graph. So note here, for acceleration, you will have VT graph instead, because the gradient of a VT graph is acceleration, which is something I should cover. Okay, if I have, so let's say I have y and x, and then I have some graph. Okay, if I were to choose a single point here, now draw the gradient. Okay, the gradient represents y over x, whereas the area under the graph, okay, so m equals to y over x, and then my area is represented by y times x times x. Oh, times x. Okay, so how do I apply this? Okay, how do I apply this? If I have a VT graph, then my gradient is going to be representing V over T, which is acceleration. My area under the graph represents V times T, which is displacement. Okay, so it's very important for you to be able to do that. So let's do that fairly quickly. Okay, first case, I will have ST. Second case, I will have VT. And third case, I will have AT. Okay, so now I'm asking the question, what does the... I can't draw a straight line, can I? Okay, so what does the gradient represent? What does the gradient represent? And what does the area under the graph represent? So if I have some weird graph, okay, so let's say I have some weird graph, the gradient here, the gradient is simply s over t, which is velocity. Okay, this is going to be representing velocity, whereas the area under the graph is just st, which has no physical significance, at least not to your level. No physical significance. It doesn't represent anything. Okay, that's what it means. If I were to talk about the VT graph, I'll have V over T, which is just A, acceleration. So the gradient under the VT graph represents acceleration. The area, on the other hand, as we've covered just now, is just VT, which is displacement. So what we say is the area under the VT graph is the displacement. Okay, now for AT graph, acceleration against time, I'm going to have A over T, right? A over T, this just means represents, okay? A over T, which again has no physical significance, okay? But my AT graph, it represents its velocity. So what we can see is that if we talk about gradient, we are referring to what's next. This is referring to what's next. Whereas when I talk about the area under the graph, I'm talking about what was before. What was before. Okay? Right. So that is all on average and instantaneous quantities. Okay? And now we move on to kinematics equations. All right, I'm just going to show a quick derivation for the 4 equations of kinematics that you will need. So let's get into it. Okay, we begin by defining our acceleration, okay, average acceleration. So that is simply going to be v minus u over some time. So let's assume that time passes from 0. So that means this is coming from, so side note, this is coming from tf minus ti, but then my ti is 0, and then my t is equals to t, so that's just t equals to 0, means it's equals to t. So let's define that. That's the first equation that you'll have. I can just rearrange this to have, I'm just going to write it in red. That's the one that you need. I'm going to write this as v equals to u plus at. That's the first equation. Okay. Now for the second equation, okay, what you will need is to consider a VT graph expressed by the first equation. So VT graph. I'm going to draw a straight line. It starts from u, and right, it starts from u, and it ends at v. Okay, I'm just going to color this. So the area under the graph simply represents the displacement. So I'm going to have my displacement is equal to, so based on rhomboids, I will have u plus v over 2 times t. Okay, a nicer way of writing this is just half u plus v times t. So that's how I would do it. Again, this is an equation that you'll need, so I'm going to put it in red. So s equals to half u plus v times t. Okay. Now, once we have those two, okay, I have one equation that relates v to a. I have another equation that relates between s and v, right? So what I can do now is I can derive another equation. I can derive another equation for between s equals as a function of a somewhat, or at least s with an a in that equation. I can have s equals to half u plus, I'm going to substitute this whole thing into here. What I'll have is u plus at times t. Okay, so then what I'll have is s equals to half times 2u plus at e. Okay, half just goes away with the u, so ut plus half at squared. Again, this is an equation that you need, so I'm going to write it in red. So s equals to half, sorry, s equals to, I need to multiply the u with the t, so ut plus half at squared. Okay, notice that in every one of these equations, on the first 3 equations at least, we always have time. But what if you don't know time, right? Time is a stranger to you. probably. Then we need another equation that relates between our velocities. We need something that relates between velocities, u and v, and then we need something that relates those two with acceleration and displacement without time. Okay, without time. So then what we do is we need to get rid of time, right? And how we get rid of time is again referring to the first one. We have v equals to u plus at. I can rearrange that again. I can have t equals to, let's see what we have, v minus u over a. Okay, and then I can substitute that into any one of these two equations. Okay, so let's choose this one. Okay, I'm going to put it into s equals to half u plus v. So s equals to half u plus v times t. I'm going to take that and shove it in here. What I'm left with is s equals to half u plus v times v minus u over a. Okay, so I'm going to have 2as equals to u plus v u minus v. So those who are a bit more keen on mathematics will notice that this is actually equals to u square minus v square, 2as. Okay, so if I can just rearrange that, I'll have v square, again equation that you need, v square equals to u square plus 2as. Okay, so summary, time for summary. The four equations that you have begins with v equals to u plus at. The second equation that you have is about displacement, right? And velocities, u plus v times t. The third is going to be with acceleration in that. So s equals to ut plus half at square. And then the last one would be v square equals to u square plus 2as. Now, you can go ahead and try to check if it is dimensionally consistent. So that means this is going to be, this is going to be ms negative 1, this is going to be ms negative 2, this is going to be s, these two will combine to be ms negative 1, these two have the same units, and therefore my v will have units of ms negative 1. They match, they are homogeneous, they are of the same kind, and therefore we know that our equation is dimensionally correct. Okay, so this is working with just one single equation. We will have to apply this into 2 dimensions, right? Okay, and we'll work this out in the 2-dimensional part of this video. Okay, so we are in the second part of we're in the next part of the kinematics equation, and where we want to apply it to 2 dimensions. We've had the kinematic equation. The 4 equations that we have is v equals to u plus at. We have s equals to ut plus half at square. We have s equals to half u plus v times t. And then we have the last part, which is v square equals to u square plus 2as. Okay, so now if we were to apply this to 2 dimensions, we'll have to break this, each one of this into x and y components. So instead of having v, we will have vx, and then we will have vy. We split them up, we resolve it. Resolve. So here we do resolving. Okay, we resolve. And we can consider the initial velocity, ux, and then we can consider the acceleration in x plus acceleration in x, and then times t. T is the same. So again, vy equals to uy plus ayt. So a specific case that we want to go through is actually for projectile motion. Projectile motion. What is projectile motion? We want to cover, right? It is simply a projectile. It is something that is in motion and it is under gravity. So it is under the influence, under gravitational influence. Okay, so one of the assumptions, or one of the things that you consider, is that the acceleration in x is going to be 0, whereas the acceleration in y is going to be negative g, or a specific direction downwards. Okay, so what happens is that, let's say you kick a ball, it will follow a parabolic path. Okay, it will follow a parabolic path, and we want to describe that particular motion. We will kick the ball at some velocity, some initial velocity. Let's call it some initial velocity. Okay, and the general procedure is that we will have some general velocity at some angle, and then we're going to split them up into ux. Okay, and we will have uy, and then we will apply the kinematics equation separately. Okay, we will apply it separately. So let's say you have ux, right? I have u going this way, I have u going this way. I want to find my ux, and uy. Okay, and I have some angle. Okay, if I were to apply trigonometry here, what I'll have is that ux is equals to u cos theta, and then I have uy to be u sine theta. Okay, that's what I'll have. Again, my ax is 0, and then my ay is simply going to be negative g. So if I were to apply my velocity equation, I will have vx is equal to u cos theta, and then plus 0, right? Because it goes to 0, right? Plus ax t, this goes to 0. So vx is equals to ux, which is equals to u cos theta. Okay, whereas my vy is going to be equal to u sine theta, so plus and minus gt. Okay, so at any time I can figure out what is the velocity of that ball in its y component. Okay, we'll cover this in a number of sample problems, but at the moment, the thing that I want you to know is, whenever you see some velocity, right, some initial velocity, I want you to immediately split them up into x and y components. Okay, of course we can expand this for displacement as well. I'll just write down the results of it, which is going to be, my displacement in x is simply going to be my ux times t, right? Because the half ax t square is going to get to 0. Here I'll have u cos theta times t, whereas my sy is going to be a bit longer, is going to be u sine theta, right, plus, sorry, times t, u sine theta t, plus half negative g t square. Okay, so that's simply going to be u sine theta t minus half g t square. Okay, so if you were to just plot these two out, sy and xx, you will get a parabolic path. Okay, because there's a t square here. The moment there's a square, it is going to be parabolic or quadratic. That's a better word for it. Quadratic. Okay, so projectile motion, right, it's a classic example of two-dimensional kinematic case. Okay, we'll do several problems in class, or even I'll probably make a video on this. Okay, now I do want to add that you can have special situations. So one of those special situations is that if you kick a ball and it follows a parabolic path, there's a point in space that which has the highest displacement in y. Okay, so This is what we call max height. Okay, this is when you have max value of sy. Okay, this happens when my velocity in y is 0. Okay, this is number one. Number two is that I can also talk about how far it travels. Okay, that's x, sorry. So this max range that we call, right, is simply max displacement in x. Okay, this happens when it returns back to its initial position, which is as x equals to 0. Sorry, as y equals to 0. You see, it goes up and it comes back down. It goes back to its initial height. So you can determine range, okay? You can determine range is when sy equals to 0. Okay, from there you can work out the range equation, and then for max height you can assume that this vy is 0. These are your general assumptions for each of the situations that you are looking for. Okay. Again, we'll look into it. All right, that is all for me in this chapter 2 video. Thank you very much.